Hello and welcome back. In this lecture, we'll learn how to containerize a simple Hello World web application. The application is written with Python and Flask web framework. The reason we choose Flask is because it's lightweight web framework and very easy to get started. You can visit Flask website to learn more about it. Don't worry if you have never used Python or Flask before. In this lecture, we'll be focusing on how to work with Docker and how to Dockerize a simple web application. We won't get into technical details about Python or Flask. Also, all the dependencies are managed by Docker, so you don't have to install Python or Flask in your local box. It should be quite easy for you to follow along. I just created a GitHub account for this course and uploaded the source code of this web application to GitHub. You'll need to have Git installed in your local box to download the source code. In case you don't, just Google Git installation and follow the instruction to install Git. Or if you don't want to install Git, you can also download the source code from the supplementary material. I already have Git installed on my local box, so I just issue the git clone command here. You might have noticed that I'm using a -b option here. The reason being I'm using different tags for various stages of the code through this course. The source code for this lecture is tagged with v0.1. So after Git downloads the repository, it'll check out tag v0.1 as a new branch for you. Now hit enter to start calling the repository. Let's see what has been downloaded. The repository is named as Docker app. We enter the repository and clear up screen. Let's check what's inside the repository. There are only a Dockerfile and a directory in this repository. The Dockerfile is used to build the Docker container for this web app. The app folder is our application folder, which holds our Python code. Just enter the app folder. There is only one file here. This is one Python program which will initialize and start a Python server. Let's check out the code. I'll quickly go through the logic of this piece of code. The first two lines basically import Flask module, initialize Flask and create the application object. The second part of the code registers a view function for a given URL/. When the given URL/ is requested, the hello world method would be called, which just returns hello world. The last piece of this code initializes and starts the Python Flask server. Just be aware that do not use this run method to start an application in a production. It is not intended to meet security and performance requirements for a production server. Instead, use UWSGI or CGI. You can Google Flask deployment options to find more information about it. In this lecture, we'll be sticking with this run method just for the sake of simplicity, as Flask is not the major focus of this course. But make sure you don't do this in production. Here, I'm using the application server at 0.0.0 instead of localhost or 127.0.0.1. This is needed if we want to have the server available externally, so that your app server can be accessed by other containers as well. Now, let's move on to take a look at the Dockerfile. First of all, it is the from instruction. We're using the Python 3.5 as a base image, which already has Python installed. Then we install Flask 0.11.1 using pip install, which is a Python package management tool. Next, we add a new user, admin. The MS option will create a default home directory for this admin user. And we're setting the default shell of this admin user to bash. The following user instruction ensures that we'll be running the app server under the admin user. In general, you should always set the user instruction in your Dockerfile to run your process as an unprivileged user within the containers. Otherwise, your process will be running as a root within the container. It is concerned that if an attacker breaks the container, he would have root access in the host machine because the UIDs are the same. In theory, a root user within a Docker container cannot escalate to be root on the host machine, but many people believe that it's possible to do so. As far as I know, it is certainly harder to do so with Docker containers because of the capacity restrictions enforced by Docker. But if security is a big concern, we should stack up multiple safety mechanisms. So as a good practice, we should use a non-privileged user to run the app server. The next instruction is workdir. This instruction sets the working directory for any run CMD. Enter point, copy, and add instructions that follow it in the Dockerfile. Here we are using /app as our working directory. Then we copy the app directory to the container. Finally, we run our Flask application. Because we have defined our working directory to be /app, so here I can just use the relative path of the app.py file. Now we're ready to build the container for our Flask application. Here we do docker build -t, name our Python app as Docker app, then tag it with v0.1. The build context is the current directory because the Dockerfile sits here. Just hit enter to start the build. It might take a while for you to download the Python base image if you have never downloaded it before, because the base image is about 600 megabytes. This is how it looks like if everything goes well. Let's check out our Docker app image by running Docker images. See? The first entry is the image we just built. It's time to run our Docker app container. Here we do docker run -d to run the container in the background. Then -p to expose the port. By default, the Python Flask server will be running at port 5000 inside the container. Let's map port 5000 on the container to port 5000 on the host, so that we can access the Python container from our local box. Lastly, just copy and paste the image ID to run and hit enter. See? Docker builds the container, starts it up at the background, and returns us the container ID. Let's access our Python app server to see if it is up running. First, we need to find out which IP the Python server is running on. If you're using Linux, the Python server should be running at your local box. If you're using Mac or Windows, Python server is running on the Docker virtual machine. You can find out the IP of the Docker machine by running Docker machine ls. See? It displays various information about the default Docker machine. Just copy the IP of the Docker machine. Then open the browser and copy the IP to the address bar. If you're running Docker on Linux, or you're running Docker for Mac or Docker for Windows, you should put localhost here. We have exposed the port 5000 on the host. So here we just type port 5000 and hit enter. There you go. We get hello world. Our app is up running. We can also log into our container. In order to do that, there is a new command to learn. Docker exec. Docker exec allows you to run a command in a running container. Let's run docker exec -it to run the command in interactive mode. Then we copy and paste the container ID. Lastly, we need to specify which command we would like to run inside the container. In this case, we run bash. Just hit enter. See? We're right inside the container and we're logged in as the admin user. As you can see, we're at the /app directory, which is the working directory we defined in the Dockerfile. We can also enter the home directory of the admin user. Here, if we do ps-exu, it displays all the running processes on this container. See, our Python application is running under the admin user, which is exactly what we defined in the Dockerfile. That's it for this lecture. I'll see you later. Hello and welcome back. In this lecture, we'll turn our Hello World application into a small key value lookup web app. We'll start with implementing this key value lookup web app as a single service. Then we will look into splitting this application into two small services and run them in two different containers. And we'll see how this naturally leads to a microservice approach. Let's take a quick look at what the simple key value lookup web app looks like. This is the front end of the application. Here we can put Arabic number 1 and English number 1 as a key value pair. Just click the Save button to save the pair. Let's save Arabic number and English number 2 as another key value pair. After the two key value pairs have been saved, we can then look up the value with a key. Let's type Arabic number 1 as the key and click Load. See? The app returns English number 1, which we saved previously. We can also look up Arabic number 2 as well. Looks like a very simple app, right? Let's see how this app is implemented. I have already tagged the source code of this application as v0.2. You can just enter the Git repository it downloaded in the previous lecture and run git stash to stash any changes you made in your working directory so that we can have a clean working directory, and git checkout v0.2. Then just open up the repository. Here I'm using a Sublime text. You're free to use your favorite text editor. Let's expand the directory structure. As you see, we have added a new template file, index.html. This file defines the layout of the web page you saw at the beginning of this lecture. Now, I'll quickly walk you through the updated source code of this application so that you'll have a rough idea about how the system works. First, let's take a look at the index.html file. This file defines the skeleton of the web page you just saw. It defines two input text fields. The first one is linked with variable key. The second one is linked with variable cache value. Those two variables are both defined in the controller, which is the app.py file. It displays two submit buttons. One is to save the key value pair. The other one is to load the value with a key. Let's move on to take a look at this app.py file. Here, we are using a Python built-in data structure dictionary to store all the key value pairs in memory and initialize the dictionary with a single entry. The second part of this code registers a view function for the URL slash for both post and get HTTP methods. If we first load the web page, this is going to be a GET request to the server. If we click the Save or Load button, the browser will send a POST request to the server. By default, the view function only handles GET method. So we need to explicitly specify both POST and GET methods here, so that the view function can handle both cases. Here we assign the default value, which is Arabic number 1, to the variable key, so that if we first load the web page, the app will display a default key value pair. If the user specifies the key in the form, we then override the key variable. Next, if the user clicks the Save button, we'll go ahead and save the key value pair in our in-memory dictionary. Then we do a key value lookup in the dictionary to get the key value pair and pass it to the template to render the HTML page. Those are all the changes we made in this controller file. The Dockerfile says the same as before. Nothing is changed. Then what we do here is to rebuild the Docker image and retag it with v0.2. Now it's time to spin up the container. Just issue the docker run command to start up the container. Let's switch to browser and refresh the page. See? Our service is up running. So far, we have demoed how this simple app is implemented as a single service. In the second half of this lecture, We'll be looking into how we can split this app into two small services by introducing a Redis Docker image. Redis is an in-memory data structure store often used as database, cache, and message broker, and has built-in replication and different levels of on-disk persistence. It's widely used in lots of critical products in the field such as Twitter timeline service and Facebook newsfeed. Let's see how we can integrate Redis into our key value lookup service. Since our application is written in Python, we'll need a Python Redis client so that our application can interact with the Redis server. You can find this Redis Python client web page by Googling Redis Python client. As you see, the Redis API is very simple. It has a GET API to look up the value with a key and a SET API to save the key value pair into Redis. So let's start with updating the app.py file to use the Redis service. First, we need to import the Redis client module. Then we can just copy the Redis client initialization code from the Redis Python client web page. This would construct a Redis client object for us. Note that this host parameter here specifies the hostname of the Redis server, which the Redis client will connect to, because we'll be running the Redis server in a separate container. Here, we just put the container name Redis here. Later, I would show you how we can link the Redis container with our Python server container. Let's put the same initial value into the Redis service. We also need to replace the Python dictionary code with the Redis API. Just update the code about saving the key value pair with Redis set API. And also update the GET API here. By default, Redis would return us a byte string which has a character B prefix. We'll need to decode the byte string with UTF-8 decoder. Don't forget to update this Python dictionary lookup code with Redis API as well. We're done with updating this controller file. Let's continue to update the Dockerfile. Because we're using the Redis client in our Python code, so we need to ask Docker to install the Redis client package for us. Just type Redis and install the latest version, which is 2.10.5. Now, we're done with the code modification. We'll see how we can start up our Python apt container and the Redis container, and how we can link them together. I hope you have enjoyed this lecture. I'll see you later. Hello, welcome back. In the previous lecture, we have integrated Redis into our application. In this lecture, we'll learn how we link the Redis container and our Python app container, which will allow them to talk to each other without having to expose any network ports. This can be done using Docker container links. Container links allow containers to discover each other and securely transfer information about one container to another container. When you set up a link, you create a conduit between a source container and a recipient container. The recipient container can then access select data about the source container. In our case, the Redis container is the source container, and our app container is the recipient container. The links are established by using container names. Let's see this in action. First, let's run the Redis image in a container and give it a name Redis, which will be used to establish the container link. Here, we use the latest Redis image, which is 3.2.0. Now, Docker is downloading the Redis image. After the download is complete, we run Docker ps to verify the Redis container is up running, and it's named Redis. Then, in the second step, we build our Python app image and tag it with v0.3. The build completes successfully. Now it's time to run our Python application container, which is the recipient container. This time we start the application container in almost the same way as we did before, except we add the double dash link option and specify link to the Redis container so that the app container can connect to the Redis container using the container name Redis. Do you remember in our app.py file, we have used the Redis container name as the host name? This is where the Docker container link's being used. Now we just hit enter to start up the container. The container starts immediately. Let's switch to browser and refresh the web page. See? The application is up running. Here we do some basic key value lookup to verify the app is functioning as expected. Great! Everything worked well. So far, we have demoed how to use Docker container links to get our app container working together with a Redis container. You might want to ask how container links work behind the scenes. I'll show you in a second. Let's log into the Python app container first. What I'll do is that I'll open the etc hosts file. When a Linux machine gets started, it will need to know the mapping of some host names of the IP addresses before DNS can be referenced. This mapping is kept in the etc host file. What you see there is an entry created for our Redis container. Here is the Redis container name and the container ID. So host name Redis will be resolved as the IP address on the left column. The IP is the IP address of the Redis container. Let's approve that. Just run docker inspect Redis container ID to inspect our Redis container. And grep IP. You see? The Redis container IP is 172.17.0.2. We can also verify that by pinging Redis inside the app container. Let's log on into the app container again and ping Redis. You see? It is directing the echo request to 172.17.0.2. Let's summarize here. The main use for Docker container links is when we build an application with a microservice architecture. We're able to run many independent components in different containers. Docker creates a secure tunnel between the containers that doesn't need to expose any ports externally on the container. You'll note when we started the Redis container, we did not use -p flag. That's a big benefit of linking. We don't need to expose the source container, here the Redis container, to the external network. That's it for this lecture. I'll see you later. Hello, and welcome back. In this lecture, we'll learn how to automate our current Docker workflow with Docker Compose. Currently, we have to start up the Redis container first, and then start up the app container and link it to the Redis container. This manual approach works well for small applications, but it would get rather impractical when the number of containers and the number of container links grow. What if our application have more than 20 components and they're all running inside containers? It would become very complicated to start and link all the containers. Here is where Docker Compose comes in handy. Docker Compose is a tool for defining and running multiple container Docker applications. So with Docker Compose, we can define all the containers in a single file called Docker Compose YAML file. We can run a single command to start up all the containers. Here is what the Docker Compose YAML file looks like. You can find this web page by Googling Docker Compose. If you installed Docker using the Docker toolbox, you should already have Docker Compose installed. If not, you can always follow the installation guide at this Docker Compose web page to install Docker Compose. You can verify if Docker Compose is already installed by running Docker Compose version command. See, it displays the current Docker Compose version. Now, it is time to write the Docker Compose YAML file for our application. Just create a docker-compose.yml file.
Docker technology evolves rapidly over the past few years. So far, there has been 3 versions of the Compose file format. Version 3 is the most up-to-date format and is a recommended format. To specify version 3, we just put a version column 3 entry at the root of the YAML.
In this file, we define the services that make up our application. For each service, we provide instructions about how to build and run the container. In our application, we have 2 services, Docker app and Redis service. First of all, let's work on the Docker app service. The first instruction we'll write is the build instruction, followed by column and dot. The build instruction defines the path to the Dockerfile which will be used to build the Docker app image. Because our Docker app Dockerfile is sitting at the same directory as this Docker Compose YAML file. Here we put dot, which means the current directory. The second instruction we'll write is the port instruction, which defines which ports on the container to expose to the external network. The port instruction is analogous to the -p argument of the Docker run command. Mapping ports are defined in host port column container port format. Here we just type port 5000 column port 5000 to expose container port 5000 to host port 5000.
Next, we need to add a depends on section to express the dependency between the Redis service and the Docker app service. Because our Docker app container is effectively a client of the Redis container, we want to start the Redis container before the Docker app service. Docker Compose will start services in the dependency order defined in the depends on section. Here in the Docker app service, we add a depends on section to let Docker Compose know the Docker app depends on the Redis service, so that Docker Compose will start Redis container before Docker app container. It's very important to ensure that services start up in the right order in a microservice world.
Now, we're done with the Docker app service. Let's move on to the Redis service. The only instruction we need is the image instruction. The image instruction defines which image to run a container from. In this case, we use Redis image 3.2.0. As you see, we can either run a container from an existing image, or we can build an image from a Dockerfile. All service would either need an image or build instruction. We're done with writing Docker Compose file. You might want to ask why we don't need to define the linking between Docker app service and Redis. This is because the version 2 Docker Compose format supports Docker network feature, which allows containers to be discovered by its name automatically. And any service can reach any other service at its service's name, so linking is not required anymore. However, if you're using the version 1 Docker Compose supports, you do need to add container linking here.
Before we use Docker Compose command to bring up all the containers, make sure we have stopped all the running containers in the previous lecture to avoid port conflict. Let me show you how to do this. First, run docker ps command to find the container IDs of all the running container. Then we run docker stop command and paste all the container IDs to stop the running containers. Now it's time to try out the Docker Compose commands.
To run the app, we simply use the command docker compose up. The up command will build the images for all services defined in the YAML file, create and start all the containers. We can run docker ps to verify the Docker app container and the Redis container are up running. Let's summarize. We have demonstrated how to automate our Docker workflow with Docker Compose command. Docker Compose is a very handy tool to quickly get Docker environment up and running. It uses YAML files to store the configuration of all the containers, which removes the burden to maintain our scripts for Docker orchestration, such as starting, linking, and stopping our containers. In the next lecture, we'll learn more about Docker Compose workflow. That's it for this lecture. I'll see you later. Hello and welcome back. In this lecture, we're going to learn more about Docker Compose workflow. In case you didn't follow the instruction in the previous lecture to write the Docker Compose file, I've uploaded the source code to GitHub. You can get the source code by running git stash and git checkout v0.4. In this lecture, I'll demonstrate how a typical Docker Compose workflow looks like. Here I'm at the directory where the Docker Compose file lives. Usually, a typical Docker Compose workflow starts with the Docker Compose up command to start the application, often followed by a -d option to run the Docker Compose command in the background. After all the containers start up, we can run Docker Compose ps to check the status of the containers managed by Compose. As you see, both two containers are up running. Another useful Docker Compose command is Docker Compose logs, which would output colored and aggregated logs for the Compose managed containers. You can also add a -f option to follow log output. It would output appended log when the log grows. Docker also allows you to output the logs of a specific container by appending the container name in the end. When we're done with the application, we can issue Docker Compose stop command to stop all the running containers without removing them. The same containers can be restarted if we run Docker Compose up or Docker Compose start command. Or if you want to completely remove all of the containers, you can do Docker Compose rm. Now Docker is asking if you really want to remove those containers. Just type Y and hit enter to confirm. Now the containers are deleted. Now if we do Docker Compose ps again, see? All the containers are gone. A typical Docker Compose workflow usually invokes making changes to the source code or images and rebuilding the containers afterwards. Let's just open up the Dockerfile and change the username to James. Now the question becomes, how can we let Docker rebuild the image? By default, Docker Compose up will only rebuild the image if the image doesn't exist. Let's prove that. Just run Docker Compose up again to start up all the containers. Run Docker ps to verify all the containers are up. We log into the Docker app container. Now we're inside the container, but as you see, we logged in as admin, not James. So our change doesn't take effective. This is because Docker Compose up doesn't rebuild the image because Docker found out the image exists. You might want to ask, how can we force Docker to rebuild the image? We need to use the Docker Compose build command, which will rebuild any images created from the Docker files. Let's give a try. See? Docker rebuilt the image and printed out all the instructions. Now let's rerun Docker Compose up. This time, Docker recreates the Docker app container because it found a new image. Let's do Docker PS. We can see the Docker app container is newly created. If we log into the Docker app containers again, now we logged in as James. So the takeaway here is to use Docker Compose build whenever you need to update an image. I have demoed a lot of Docker Compose commands in this lecture. Let's review what we have learned about Docker Compose workflow so far. Docker Compose up starts up all the containers. Docker Compose PS checks the status of the containers managed by Docker Compose. Docker Compose logs outputs colored and aggregated logs for the Compose managed containers. Docker Compose logs with -f option outputs appended log when the log grows. Docker Compose logs with a container name in the end outputs the logs of a specific container. Docker Compose stop stops all the running containers without removing them. Docker Compose RM removes all the containers. Docker Compose build rebuilds all the images. That's it for this lecture. I'll see you later.